So welcome. We will start this lecture with a concept of tensor algebra and Lie derivative with respect to this tensor algebra. That what is it? It is a useful concept, rather well involved, but not too much. That is useful in expressing several properties of some operators, including Lie derivative, and some modification of this tensor algebra will be next year in connection with differential forms. It will be also very useful, also in connection with some very useful operators, that to express abstractly some properties, for example, of Lie derivative, and then also to make easy proofs of some identities. Like we will show today that there are two properties of Lie derivatives. I will write them here in advance, but I will prove them after this concept of tensor algebra. That Lie derivative in the direction of a linear combination turns out to be the appropriate linear combination of the two Lie derivatives. And also Lie derivative in the direction of a commutator turns out to be commutator of Lie derivatives. Extremely useful formula. And that is just composition minus the opposite composition. Yes, so this formula turns out to be very useful, also this, and the proof of them without these properties of how it behaves with respect to some tensor algebra is too complicated, and with this property it is very simple. So what is a tensor algebra? First, there is something abstractly denoted like A. It is associative algebra. We already had it because we had some examples. What is it? It's a linear space. So elements can be linearly combined and bilinearly multiplied. Yes, this is called associative and bilinearly and associatively. So A, B, C equals A, B, C. This is this associativity, and bilinearity we know what is it. With respect to this linear combination, of course. So the basic examples were matrices of so square matrices with respect to linear combinations and standard matrix multiplications, and functions on anything but on manifold in our case. R-valued functions, say, also C-valued functions. Here is pointwise multiplication and so on. Now, there is a question that we have tensor fields on M, and tensor fields can be also linearly combined and multiplied in tensorial way. This multiplication is associative. There was an exercise. Also, it is bilinear. So it looks that all tensors also fulfill it is possible to invent some algebra of all tensors. Yes? But what is not known, that this is not defined for various tensors, for different tensors. This can be done from any PQ and P prime, Q prime tensor. Yes? But this is only defined for the same type of tensor. So the problem is this structure for all tensors, and this is in the context of tensor fields, it is just T00. So we see that T00 as a part of all tensors is algebra, but all tensors are not yet algebra because we are not able to make linear combinations of different type of tensors. And to save this, there is a simple construction, and after this construction, it will be already okay. And we, after introducing what is linear combination of various types of tensor, we obtain something which is called Tm, and it will be a nice algebra. And in this algebra, there are nice operations which have some properties, and Lie derivative is one of them. Yes? So this is useful structure also for studying Lie derivatives and their properties. So what about this linear combination? Actually, we already have or know this trick, but we didn't do it maybe in sufficient detail. That imagine that we have two vector spaces, L1 and L2, and we mentioned in the context of representations that we can do the direct sum, sorry. This is a direct sum. What is the definition? That elements from this direct sum are pairs of vectors where V1 is from here and V2 is from here. So elements are pairs. That means that it is a Cartesian product as a set. And what is the definition of linear combination? It is claimed that it is a new vector space. So a linear combination should be defined. So by definition, linear combination of two elements is defined as V1 plus lambda W1 and V2 plus lambda WT. And you should check that it works, simply, that it is a well-defined linear structure. All axioms are satisfied. Now, what is interesting, that if we study elements of this structure, call them L1 tilde, they are elements of some linear space. If you apply this linear combination, you will see that those elements are is a subspace of the whole space. Yes. And the same with 0v2. And it is a canonical construction. We have pairs, special pairs v1, 0 and 0v2. It is a canonical construction. It doesn't depend on some arbitrary choices. So we have, whenever we have this linear space, we have canonically inside some subspace, which is clearly isomorphic to the L1. So this is isomorphic to the original L1, and this is isomorphic to the original L2. Well, the isomorphism is the correspondence, for example, this. Yes, for the first isomorphism. And what it means, that we have inside L1 plus L2 a space which is canonically isomorphic to L1, and another space which is canonically isomorphic to L2. And if we have something canonical isomorphic, we can identify these two spaces. So we can say that this is the same thing like this, like we did several times already. For example, we because we found canonical isomorphism of L and L with 2 stars, the second dual, we don't speak of elements of second dual, we just speak of elements of L. But they are actually elements of second dual sometimes. Yes? So in the same way, we can now speak that whenever we want to speak of elements of L1, we can speak of elements of L1 tilde. And so now, if we have a linear combination of those guys, it is clear that it can be done, yes, because here is the formula for arbitrary elements. So in particular, this can be done. But this is isomorphic to V1. This is isomorphic to V2. So effectively, we are doing V1 plus lambda V2, which is, as it is written, officially forbidden, yes, because they are elements of different vector spaces. But now they are embedded in bigger vector space, some common vector space, in which it is already officially possible to do it. So the idea is that simple. And I already mentioned that it is the idea that you can make a sum of what? Of a pear and apple, which was forbidden for a long time, and now you are freedom that do it. It is officially allowed from today. Yes, that something. It is what officially? It is a pear. That an apple 0 plus 0 plum, not plum but pear. It is the sum. So do not be afraid to add apples and pears. It is now possible. Even you can make iterated construction and make summation of this and cheeseburger, for example. I do not recommend it because I am plant-based, yes? So I do not recommend, but I must admit that it is possible from today. So after this idea, which is hopefully quite clear, we see that we can make sum of covector, vector, and metric tensor in a big space, which how this big space looks like. It is this tensor algebra, which is product, or sorry, it is a sum over PQ from 0 to infinity of TPQ or TPQM. So formally we do it from 0 to infinity. So for all PQ types we sum, we make infinite direct sum, which is of course dangerous from the point of view of functional analysis, because there we are summing infinite dimensional linear spaces, and there are infinite number of them. But we will use it only for finite sums, yes, from now on, like that. And what kind of multiplication is now there? For example, this cross G plus F. This is one element of this tensor algebra. It is sum of covector and vector. Here is another element of tensor algebra, the sum of metric tensor and a function. It was not possible yesterday, but today it is also already possible. And now, what is the multiplication? Well, first with second, and so on. By definition. And these particular multiplications are of the type of standard tensor multiplication. Yes, because here is tensor multiplication of a covector and function. We know what is it. Here is tensor multiplication of vector and metric tensor. We know what is it. So, but here is multiplication of something which should be defined. It was not officially explained what is it. Now it was officially explained. Yes. So, possibility of adding any types of tensor and multiplying of such groups, such sums of various types of tensors in this way actually creates something which is called tensor algebra of manifold M. It is canonically associated with any manifold M. Whenever you define some manifold M, the tensor algebra of this manifold is already given automatically. It is canonical object associated with any manifold. So we can now say that we have an interesting algebra. And it turns out that this T00 is a subalgebra in this algebra. What is a subalgebra? It is a subspace which is also closed with respect to the multiplication. Yes, that you do not go outside. If you have some subalgebra, some subalgebra, it means that it is algebra itself and it is subset of this bigger algebra and it is closed with everything which is defined on algebra. That means linear combination and multiplication. And nice example is this as a subalgebra of Tm. Yes, of course it is a subspace, but we know that by multiplication, tensor multiplication officially of two functions, we obtain just a function. Yes, so it doesn't go outside this T00. Now, in the language, if algebra, which we already have an interesting algebra for our purposes, we can study interesting operations. First, automorphisms. So what is it? It is, as the title already says, it is mapping of algebra to itself, which is bijection, and it preserves everything what is there. And what is there? Actually, linear combination and multiplication. Yes. So psi on A plus lambda B is psi A plus lambda psi B, and psi of AB is psi A psi B. Notice that the multiplication is the same multiplication. Here is something, multiplication in the algebra, and also this is multiplication of the algebra because we go from algebra to algebra. It is automorphism. It is isomorphism on itself. Now, what kind of automorphisms we have on our algebra? Imagine we have a diffeomorphism of a manifold. Then pullback with respect to this diffeomorphism is a mapping from TRSM to TRSM for any RS, so it can be also treated like a mapping from Tm to Tm now, yes, after the realizing that Tm is a part of bigger structure. And what are properties? That it is an automorphism. Important. Where from we know it? From one exercise which was already on recitations. Maybe it was not chosen, but it was in the offer. I have no number of this exercise here, but have a look that this, actually what is to be proved, that it is from Tn to Tm, we know, and that it is linear and it preserves tensor product. Yes? Whenever, if you prove that, and this is the thing which is to be proved in some simple exercise, then we realize that it can be treated as that pullback induces an automorphism of a manifold. Pullback of diffeomorphism, yes? Not all pullbacks. And there is another interesting, these automorphisms, if you have two of them, then you can compose, for example, in this order, and you easily check that the composition of two automorphisms is again automorphism, clearly. So, and there is identity mapping, which is automorphism. Because it is bijection, you can inverse it. It is also automorphism. So we obtain a group of automorphisms of any algebra. This group is also canonically associated with this algebra. Yes, so for example, also here, the group of automorphisms of Tm form a group. It is a group, all automorphisms, any algebra. And there is another interesting mapping from A to A, which is called derivation. Of A. So not derivative, but derivation. It is algebraic concept. And it is mapping from A to A such that it preserves linear structure. That means it is a linear mapping from A to A. And on product, it behaves differently. It doesn't preserve the product, but it behaves in Leibniz way. So any linear mapping which behaves in this way on product is called derivation of algebra. So if you have, for example, 2 by 2 matrices, it is an algebra, you can try to find all derivations of the algebra. It is quite nice exercise. Somehow to characterize all of them. And by the way, it is important in so-called non-commutative differential geometry, that in non-commutative differential geometry, this algebra of functions is replaced by some non-commutative algebra, and all these algebraic structures are emitting on this case. So, for example, vector field is a derivation of our algebra, because vector fields are derivations of this algebra, in differential geometry. We will see in a moment. So this concept of derivation of algebra is very, very important. And here, now, we can study derivations of our interesting algebra. So, what they are? Linear operators on tensors, which behave in Leibniz way on tensor product. And we know that we have a nice example. It is not, I don't claim that it is the only example, but Lie derivative, we know that have this property, has this property, Lie derivative, with respect to any vector field. There are infinite number of Lie derivatives. For each vector field, there is a Lie derivative. And all of them behave in such a way that we can say that Lie derivatives are derivations of algebra of tensor fields, yes? Or tensor algebra of the manifold. Derivations, in this sense. Now, how can we use it? How can we use to prove this property? Well, maybe I will add one property which is not of this general scheme, but it is specific. This tensor algebra, from this definition, where is the definition? It is already away somewhere. That what is Tm, once again, is the direct sum of all PQs, T, P, Q, M. Now, as we see, all members of this direct sum are characterized by two integers, P and Q. Now, integers, together with plus operation, form a group. Yes, this first observation. We know that there is a group of integer with respect to plus. Then, so usually, I will call them just Z here. Now, there is a construction that product of two groups. So what is this group by definition? It is composed from a pairs, one element from here and another element from here. And what is the multiplication in the group? It is multiplication of first element, comma, multiplication of second element. So here, what is the multiplication? Plus. It is P plus P primed and Q plus Q primed. This is also a group. Z is a group, and Z cross N, Z is also a group. Yes? Group of pairs of integers. And now notice that what property has tensor multiplication? If you multiply PQ tensor, so it has this property that tensor multiplication of a tensor of type PQ and P primed Q primed is from P plus P primed Q plus Q primed. What does it mean? That it copies this rule somehow, right? In this sense. That there is a rule for Z in a multiplication in Z cross Z group. Here we have association that PQ, the type of the tensor, can be associated with some element of Z cross S. This type of tensor can be associated with this element. Now, tensor product makes from these two tensors other tensor which is exactly here. So this is officially named that we have Z cross Z grading in our algebra, that it is graded algebra. It is graded by this group. What does it mean officially? That this algebra is direct sum of some subalgebras which are labeled by element of this group. This is T0, 0 plus T1, 0 plus T0, 1, and so on, 1, 1, up to infinity. So we can identify here elements of group Z cross Z, these two numbers. So we have a direct sum of subspaces, and each subspace is labeled by an element of this group, by a pair of integers. And they are summed together. And if you multiply some particular elements which have these numbers, P and Q and P primed, Q primed, such elements are called homogeneous. Homogeneous elements are elements from this Tm which are only sitting in one of these subspaces and zeros outside. Yes. So, for example, metric tensor is homogeneous element in tensor algebra because it is a tensor of type 0, 2 and not mixing of many tensors. Yes. If some element of Tm is not linear combinations of various kind of tensors, it is called homogeneous. And if you multiply, and homogeneous elements have something which is called degree, and this degree is the element of the group. So in our case, the degree is a pair PQ. So, for example, metric tensor has degree 0, 2, because it is a tensor of type 0, 2. In this formalism, it can be said that it is homogeneous with degree 0, 2. And now, if you multiply homogeneous elements, the degree is given by the result of multiplication of your group, as we see. Yes? If we multiply tensorially element which is labeled by PQ with element which is labeled by P prime Q prime, from the definition of tensorial multiplication, the resulting element has this degree, but this degree is just the multiplication in the Z by Z group. Yes? So then we call that our algebra is Z cross Z graded altogether. That first, here we see that our vector space is graded, and from here we see that also the multiplication behaves friendly with respect to this grading, namely that the result of product is labeled by the result of this product. Yes, this is named that our algebra is Z cross Z graded. And the grading is the phenomenon. Yes? That if it is graded, we speak that there is in this algebra Z cross Z grading. So it is not just an associative algebra, but it is associative algebra which is Z cross Z graded. It is more detailed structure. And next year we will have similar construction from very special tensors which are called differential forms. And there we will see that there is also algebra of differential forms, which is just Z-graded. They are not two labels, because they are tensors with 0 here and something here, plus some other property. That's why it makes no sense to say that we have just elements 0 something, so we just say about this something. And this something is Z. Yes. But now we have Z cross Z graded tensor algebra. And what, for example, this derivative does, it preserves the grading also. Yes, this Lie derivative. What does this mean? That if you go to some particular subspace, you stay inside when you apply LV. That you do not change the type of tensor by this LV. Yes? Because we will see next year in this graded algebra of forms that there are interesting operators which change the degree of the element. That if we will have some tensor of type 0, 3 and apply some operator, you obtain tensor of type 0, 4. Yes? But our Lie derivative does not this. It preserves grading. So it has many interesting properties with respect to this tensor algebra. We have a lot of properties. We know a lot of properties of LV. Now there are new properties which were not proved yet, but they will be proved. But the proof is the best proof or the simplest proof is when you use some ideas from this tensor algebra and grading and so on. And what is the idea? That if you have this LV, which preserves grading, as we know, then we can ask that what is the necessary, one more property that imagine that our A is already graded. But no, speak directly of Tm, not with this A. It is possible, but now we know that we have some particular A which is called Tm. So let's speak with properties of just of Tm. That what are important properties of Lie derivative now, because we are concentrated on derivation of this algebra, which is Lie derivative, that it is linear, then it behaves nicely, namely by Leibniz, on products, Leibniz, and it commutes with contractions. We already know these properties. They are derived from some properties of pullbacks. Yes, pullbacks with respect to, by the way, phi t, m to m, is a diffeomorphism. So phi t is an example of this diffeomorphism. And then it means that phi t star is automorphism of Tm, and Lie derivative is a derivation of Tm. But not only it is a derivation, but it is a derivation which commutes with contractions. There is an operation of contractions in our algebra. It may not be present in general algebra, but in our algebra there is something called contraction. And our derivation commutes with contraction. It is an independent property. And from these three properties, we derived yesterday how to compute Lie derivative of anything, maybe you remember. And we came to conclusion that it is enough to know what is Lie derivative of a function, that it is V applied function, and Lie derivative of d of function. And it is d of Lie derivative of function, which is v psi. That Lie derivative commutes with d. By the way, d is an operator in this algebra which changes the degree. It comes from 0, 0 to 0, 1. Yes, and it is important element on our computations that d is interesting operator which changes the degree in this tensor algebra. So not everything preserves. When we use the second property, we wanted to compute Lie derivative of a component coordinate basis. Yes? And after using this, we came to conclusion that it is Vij dxj. So we used these two properties in order to compute this result. And we also used the third property in order to compute what is Lie derivative of the basis vectors. It was something yesterday. And when we compute Lie derivative of arbitrary tensor field, we used these three properties to show that it is enough to know what is Lie derivative of this guy, and this guy. Yes? You remember, perhaps. Function, d of function, and something else, like function and d of function, but with this property, we also computed this, not directly. It can be also done directly from definition, but it is much better to realize that these two guys are mutually dual bases. And using this property, that how this property was used, that alpha beta is C of alpha cross beta. Not beta, alpha v. But here we need, what Lie derivative does on function, how it behaves with respect to contraction, and how it behaves with respect to tensor product. So these three properties are enough to say what is Lie derivative of any vector field, actually, yes, from here, including the basis vector field. So now it is quite important that from these three properties, everything can be done if you know these two results. What does it mean? Lie derivative is a derivation of tensor algebra such that it is fully given if you know how it acts on functions. That means how it acts on t00, 0, and how it acts on d of functions, which is t01, but even special element. Yes? So if you want to prove, like here, what do we want to prove? One knowledge is yet not said, and it is important, that there is a simple exercise that imagine that you have two derivations of associative algebra, yes, di a to a derivation. Then there is a simple computation that imagine this object called commutator. It is definition. Here there are linear mappings So there is just composition and linear combination of the compositions. So allowed operations with linear operators. Yes? And the claim is that this is some D3, that whenever you have two derivations of your algebra, you can construct commutator of them and you obtain the third derivation. So important thing is that it is a derivation, and even that it, if D1 and D2 commute with contraction, if there is something like contraction in your algebra, so this D3 also commutes with contractions. So if you have two derivatives commuting with contractions, their commutator is again a derivative commuting with contraction. What does it mean that what structure we have for these derivations? That what they form all of them together, if we can do such thing, and of course we can do such thing. They are linear operators. So what? Lie algebra. So derivations commuting with contractions form Lie algebra. There is a Lie algebra of derivations commuting with contractions. Yes, this is very important. And this is proved by direct calculation, that how this D3 behaves on product. Yes, for example, if you act by the first part on product, what you get from here, because it is a derivation, you get D2 applied to A multiplied by B plus A multiplied by D2B. Now this is linear operator, so it is applied on this guy plus applied on this guy. When applied on this guy, it sees product, so it acts like derivation by Leibniz. So you will have 4 terms altogether. Yes? But also here you will have 4 terms, and there is some minus, and if you write all of them, you will see some cancellation, and you will see that this element called D3 is also a derivation that is nicely behaved, according to Leibniz, on the product. It will be quite nice if somebody will do explicit computation on exercises and show us. And also it is clear that it is linear. Yes, and think that commutation with contraction is completely trivial. So linearity is trivial, commutation with contraction is trivial, and the behavior on product needs some 2 or 3 lines, nothing more. So it is not completely clear, but after 2 or 3 lines it is clear. And it is very important observation, because, for example, here, this can be written as D1 and this can be written as D2. Then, of course, here we have commutator. And what is here? It is also Lie derivative, which is also D. So let's call this D4. And this is D3, yes? So we see that this lemma or theorem, or what is it, that this is true, has the structure that some D4 equal to some D3. So it is a claim that 2 derivations are equal. 2 derivations commuting with contractions are equal. And what does it mean? They are equal on any tensor when applied. Yes. But the proof is not needed on any tensor. Yes. Because we know that if 2 derivations commuting with contractions are known how they act on functions and these of functions, they should be necessarily identical on any tensors. Because from these two give us full information of this D. This complete D can be constructed when you know what D does on functions and D of functions, in our case. Yes? So, what is enough? It is enough to prove 2 statements, whether it is true on functions and whether it is true on D of functions. And if you write it in detail, you will see that there are very simple problems, which you can prove very easily. And the answer is yes. But what is important, that after these two very simple checks, you actually checked that it is true on any tensor field. And imagine that this proof will not be possible. To prove that this is the same like this, acting on general tensor field. You know how complicated is the formula on PQ type tensor field. So to prove it directly on general tensor field, it is horrible work. But fortunately, with the help of some algebra, of some concept of tensor algebra, derivations and automorphisms and so on, we see that actually the proof is, to prove a rather complicated theorem, it is enough to prove two very simple things. Okay, so I think that I will not do this proof. It is quite simple, and I will give it for exercise. It is our 18 minutes for one student is even too much for this proving, but it is interesting result, so I will give it as a single exercise for 18 minutes to show us that this equal to this on functions and d of functions, because it is very important. Of course, together with understanding that it is enough for proving the general situation. And now I will go to other topics, which is the geometrical interpretation of commutator. Yes. It is very important and interesting to understand where you can see a commutator of two vector fields and what it means if the commutator is zero or non-zero. Because, for example, we mentioned yesterday that the commutation relations for angular momentum in quantum mechanics are actually result of commutation of two vector fields. Yes, so already in these commutation relations, Li, Lj, commutator equals I epsilon ijk lk. This I is not nice here, but it is because these vector fields are multiplied by some i's. So there is some complex situation, but it can be written without this IH in front, and then you will have without this I the result. So what it means that actually geometrically. So imagine we have two vector fields because we want to compute commutator. So we have such structure that manifold and two vector fields there. And we know that we can define flow of both of them. So we have two flows, one flow for vector field V and one flow for vector field W. Now imagine that we have a traveling agency here sitting on M, and it offers you two trips. The first trip is that go along vector field V, that means go along this flow for time epsilon. It is rather humble, but quite nice. Epsilon is long, you come here. Then turn to the other flow and go away again epsilon. It is along W. You come to some point, and there is another travel agency which offers the opposite travel, that first go along W and then go along V. And the question is whether we go to the same point by these two traveling agency or not. We will see that not. The alternative way, the third travel agency, offers something like this, 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 and this. So here V, here W, here minus V, and here minus W. Yes? So make first this step of epsilon, then this step of epsilon, then this step with minus epsilon, and this step with minus epsilon. The logic says that we should come back to our original place. Yes? We are going along V, along W, along minus V, along minus W. So we are used to think that we come to the origin, to M again, but we will see that not. There is some gap there. And this is the gap can be filled to some degree of accuracy with exactly commutator. So we have two vector fields, this path, which is not connected, the end is not connected with the origin, but if we add the fifth flow, which is flow of the commutator vector field with some appropriate time, I will show the exact formula, then we can fill this gap to some accuracy. We'll compute with some degree of accuracy, and if you do it more accurate, this computation, you will see that there is a difference still in a higher accuracy. Yes? So this is nice computation to show that how nice is to have a formula for exponent of Lie derivative. We will use it. So what is the formula? That phi t v star, it is formula from yesterday, can be written as 1 plus t L v plus t squared over 2 factorial LV, and so on. And of course the same formula for W. So the pullback of any flow can be written as an infinite series which are composed from products of Lie derivatives. And we can say that it is exponential altogether. It is e to t LV, and this is e to t LW. But we will not use the complete exponential. We will compute to some accuracy, namely phi epsilon, because if this is M, this point is phi v epsilon M. Yes? And this point is phi epsilon W applied on phi epsilon V applied on M. Yes? And similarly, here, this is what? It is phi epsilon W applied on M. And the last point is phi epsilon V applied on phi epsilon W applied on M. So we see that the order is changed. Yes? Here is this, and here is this. And the statement is that applied on the same M, the results are not the same. Or, in this logic, we have first phi epsilon V after phi epsilon W, then composed with phi epsilon minus V, then, or minus epsilon V, it is the same. You see it from this formula, that if you change the sign on T or you change your sign on V, it is the same. And the last is phi epsilon minus W. And the claim is that this is not identity. So this is not identity, but the claim is that if you help it a little bit, it will be my identity. And what is the necessary help? That here you add phi epsilon square minus, or epsilon minus epsilon square, it can be written, and commutator. So I will write minus epsilon squared. And now, after the last step, it is already 1 within epsilon squared accuracy. So if you compute it with terms epsilon to 0, epsilon and epsilon squared, this is identity. That these 5 steps are identity. That means that if you apply it on M, you will come back to M. So this is the most important fact, that there should be a correction to these 4 terms, which are somehow natural for our thinking, that these 4 terms should be identity, but not. These 4 terms should be corrected with some 5th term. And what is important, that the flow is higher order flow. It is epsilon squared flow. So it is even much shorter. So there is not big difference. Here is epsilon, 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 but here is epsilon squared with some flow, yes? And now, how to prove it? We will prove it with these formulas. So for epsilon, it is 1 plus epsilon, for example, here LV, plus epsilon squared over 2 factorial LV, LV, and so on. But there is a problem that here is some statement without stars, without pullback, and the formula is only for pullback. Yes, we have no formula for directly this flow. We have formula, nice formula, for its pullback. So there is a cheap trick, very, very nice, that do your computation simply in coordinates. That study, for example, not M goes to phi epsilon Vm, but xi of M goes to xi of phi epsilon Vm. It's clear that it is the same. If we describe it abstractly in terms of points, what points are doing, or in local coordinates, what local coordinates of these points are doing, it is the same information for us. Yes? And what is the benefit from this turning to coordinates? That what is here? Here is a function. And this function is composed with the flow. So here is actually this composition. Here, applied on M. But what is this? This is pullback of this function. So this is the main observation, that when we turn to coordinate expressions of our flows, we can use this pullback of our flow. And for pullback of our flow, we have nice now approximative formula. So what is this? It is 1 plus epsilon Lie derivative plus epsilon squared, 2 Lie derivatives, and so on. So what is it? This is just a help. The result is xi plus epsilon Lie derivative of xi plus epsilon squared over 2 Lie derivative of xi, and so on. And by the way, in particular, this Lie derivative is just v applied on xi, because we know that xi is a function, and we know how Lie derivatives of functions are computed. So now we can say that this step in coordinates can be described like that xi of this m goes to xi plus epsilon Lie derivative applied on this plus epsilon squared over 2 Lie derivative of Lie derivative applied on x, and so on. We can do it in within any accuracy we need. So when we, for example, want to compute in coordinates this step, what it means, xi of w composed with epsilon v applied on some m, yes? But what is it? It is the bracket with star, so pullback of xi. Now here, it is a pullback of composition. We know what to do. There is a formula. That is a composition of pullbacks, but reversed. Yes, we know how to work with pullback of composition of two maps. And now the finishing, this is 1 plus epsilon Lie derivative with respect to v plus epsilon squared Lie derivative 2 times with respect to v. And what is here? 1 plus epsilon Lie derivative with respect to w plus epsilon squared over 2 factorial Lie derivative with respect to w squared plus higher order terms. We can use as many terms as we know, as we want. So you can imagine that in order to do all 5 members, you can proceed in similar way. Okay? That this phi put to, or this 5 put to the bracket, then xi of this will be the bracket with star, pullback of the bracket. It goes as pullback of individual terms, and all individual terms can be written as these objects like something like Taylor expansion. Yes? And now the only thing is to compute with given accuracy this big result. You see that what is the claim? That try to compute this first to order epsilon and then to order epsilon squared including. If you want, you can compute it to with accuracy epsilon to 3rd power, but it is not necessary. What is interesting that, for example, you see that if you stop here, this term is completely out of game because it is already epsilon squared. So if you compute this accuracy, this is not here, And in order to compute with this accuracy, these 4 terms, this last term is not necessary because it is epsilon squared already. So you have just 2 terms in each bracket, and it is a simple method to learn what is the epsilon to 0, what is epsilon to 1, and nothing more is interesting. And when you do it, you will see that it is already 1. Yes, all epsilon accuracy terms cancel mutually. So these 4 guys with this accuracy give you unit operator. What does it mean? That if you do these 4 steps and compute it only to epsilon accuracy, you will learn that you come back simply, because it is unit operator applied on this M, or unit mapping. It should be mapping, yes, identity on M, because it is on point here. The operator 1 is when we do pullback. So there is nothing specifically interesting if you compute it to accuracy to epsilon. But now make it better and compute turning seriously or taking seriously also these terms. So there are a lot of possibilities how to create them, because, for example, you can multiply this by this. Yes, it is one possibility to obtain epsilon squared. Or this and this. And so you must be careful to find all possibilities. And you will see that this is not identity, because there is something near epsilon squared. But when you add this something is cancelled and you have identity. So this is exercise for recitations. It can be easily done in 18 minutes. And it is very useful. So if somebody will do it for us, so we will be very grateful to see how it is done. Of course, I recommend to do it, and everybody of us should do it himself or herself. So, this is the interpretation of commutator. Important. What the commutator does, that its flow closes this gap. And so there is a gap in this way, and it is closed exactly by commutator. This is the role of the commutator in the nature. Yes? That everybody wants to do something useful. So commutator does very useful way that closes this gap in this path. It can be even done in more complicated way, that there is an alternative identity from more pieces to obtain identity with some flows with V, W, and this flow, and some iterated commutators and so on. So if you compute with higher accuracy, there are more identities. It depends on the accuracy of your computation. And they are quite useful. They can be used, for example, in robotics, in some specific situation that there are non-commuting operations, which are flows. And it is interesting to know that what set of operations is needed to close some ways which are not closed before some additional terms or without additional terms. Now, let's have an example on it. We know already of 2 vector fields which do not commute, from yesterday at least. Maybe it is older story, but I did the computation yesterday that if we are in standard Euclidean plane, we can have vector fields which are, this is coordinate vector field, and this is vector field which is not coordinate, because it is some function times coordinate vector fields. And what is important, that we did computation of commutator, and we saw that the result here was minus 1 over r squared and this vector field, as far as I remember. Is it true? Now, it can be written, because of this definition, like minus 1 over r only and e phi. So this is orthonormal basis. And this is coordinate basis or frame. Yes. So when you make from coordinate basis based on polar coordinates an orthonormal basis, it is already not coordinate because it has non-zero commutator. We treated it yesterday that whenever you have non-zero commutator, it cannot be coordinate frame, because simply coordinate frame as a vector field do commute, because we know it from that partial derivatives commute from the first year. So now we can try to understand geometrically what happens here, that we have non-zero commutator. So what is this path using V and W of our vector fields? We are somewhere here. So here is phi and here is r. Now, if this is V and this is W, so we see that this is W here. We have a flow along V step epsilon. Yes. So where we are going? Because our two fields are orthonormal, their length is 1, and when we go a flow of along these fields, which have length 1, we just go the length epsilon. I already explained it sometimes. Is that if you have flow with respect to V, you go from M to phi epsilon V, and the distance between these 2 points is epsilon and V. So if our V is unit vector, the distance is epsilon. The flow with parameter epsilon makes distance epsilon between these 2 points. So what are the directions of ER and E phi? Here is ER and here is E phi. And both of them are unit vectors from the construction. So now the statement is that if you go epsilon in this direction, then distance epsilon, not parameter, but distance epsilon, say like here, then distance epsilon here, this is the same epsilon, so the length of these two pieces are the same, and then back epsilon in the direction to origin, and then the step epsilon in the direction of less phi. Yes? You will come here, of course, yes, because we have a situation like this in coordinate frame, that if here is phi plus epsilon, we see that this is longer than this. Yes? So if we go along here along this vector field and here epsilon along this vector field, and then back, we really come to the origin, because it is r phi, the first step, r phi goes to r plus epsilon phi. The second step, add epsilon to phi. The third step, subtract epsilon from r. And the last step, subtract epsilon from phi, that means from this phi, and you are in the same point, at the same point, yes? When you go along this minus this and minus this. But if you replace now the vectors by orthonormal vectors, you go by distances epsilon. And it is clear that if you go this distance here and this same distance back, so you finish in other point, not at the origin. And this is proportional to epsilon squared. And according to our knowledge, we should put what? Phi minus epsilon squared and commutator. So the commutator is here. And you should minus E phi means that you should go this way. So E phi is this way, minus E phi is opposite way, and but here is minus epsilon squared. So altogether it is plus 1 over r I phi step and epsilon squared. And you can check it by elementary computation that it works. Yes, that this formula that compute where you are after these 4 steps. It is easy to compute. Then check that you are not at the origin. Yes? Then compute the commutator and add this step to your picture, and you will see that you are exactly here. So you can verify this general situation in this simple example. And there is also another simple example, very similar like that. And this happens on the globe. So we believe that we live on the sphere. It is our belief. We have right to this belief. And here are these lines, meridians. And we can go first to the, say, from this point, first to the south, then to the west, then north, and then east. When the believers in the flat space see something like that, yes, in the plane. So again, well, first, second, third, fourth. Now, if you go 1 kilometer, which is epsilon on the globe, 1 kilometer, if you go 1 kilometer south, then 1 kilometer west, then 1 kilometer north, then 1 kilometer east, of course, you will not finish in the original point. Yes, because these lengths are not the same. These are the same, but these are not the same. So, in coordinate frame, theta and phi, it is here, 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 here. You finish at the same point. But if you have E theta and E phi, which are normalized to unity, so what is this? It is 1 over r derivative with respect to theta. What is this? You can check it from g equal r squared d theta plus sine square theta d phi. This is the metric on the sphere of radius r, induced from R3. So this is, from here we can easily see that the orthonormal basis E theta E phi, where this is 1 over r sine theta derivative with respect to phi. Yes? So it is not just coordinate basis, but there is some help needed to this coordinate basis. Now you can compute E theta E phi, and it is not zero, it is some vector. So when you go 1 kilometer, 1 kilometer, 1 kilometer, 1 kilometer, you finish somewhere here. So probably this commutator is, this vector is E phi in this direction. Yes, phi goes there. So you can check once again the validity of this five steps formula, that you can compute in elementary way that what is here, the length, and then you can check it from our formula and to see that it is really this difference. And also, so this is second example. The third example is from these commutation relations. So if we define these vector fields without this I mean this complex I, without minus IH or something like that, we will obtain ijk of a k if Li is epsilon ijk xj derivative with respect to k. So for example, L1, L2 commutator is L3. And now here is something which is not zero. So we can apply our formula that if you start somewhere and then act by small flow of this L2 and then small flow with L1. What does it mean? Small flow of this is small rotation around y-axis, x2 axis. The small flow of this is small rotation around the first axis. So now you should combine them, two small terms, and there is a way like that rotation around y, rotation around x, backward rotation around y, backward rotation along this x, and we see that because this commutator is non-zero, we see that we do not come to the original position. But we can fill the gap by small, higher order small rotation around z-axis. It can be visualized practically, yes, by some things that do this rotation and so on and see it. It needs some way to seeing things in R3, ability to seeing, but you can see it, that you can improve the gap between these two steps by one small step, which is rotation around z. I don't know why it didn't. Oh, it is 1 o'clock in the night. So I am afraid we will not wait to 1 o'clock in the night to hear this guy. So thank you. It is the end.